This is actually, I mean, we have the full 3D flow around this vehicle. These data sets were used when the shuttle was flying in order to do debris trajectory analysis. If they saw any foam or ice shed from the vehicle during launch, you probably are aware that was a real issue with the shuttle. They try to narrow down the position of where the debris was released and the time. They pull the appropriate data set here and then basically do debris tracking through this flow field to see if there was, to try to ascertain the probability of a strike somewhere on the vehicle. Okay, but we're not flying the shuttle anymore. Okay, this is actually a live rendering here. This is
So you solve without approximation. Now you basically simulate Navier-Stokes without approximation in 3D.
Oh, there's all sorts of approximations.
Ah, okay.
So in particular, the turbulence, you have to fudge on the turbulence because you can't resolve all of the length scales. So if you resolve all the length scales, that's DNS, right, the correct numerical solution. So this is using some algebraic turbulence model. So at some length scale, they have to kind of just approximate what's going on. But for this kind of regime, probably reasonably accurate. I'll show you some more complicated flows where the turbulence is a real issue.
Chris, I didn't mention to them what the size of the system is.
Oh, okay.
The numbers.
So the size of the system upstairs, it's 1 3/4 petaflop peak now. It's 125,000 processors.
Are you running Linux?
It's running Linux. Yes. It's all
Real
big,
fast.
It's all a big Linux cluster.
All right.
So we're running SLES. So I think we're going to move to CentOS. So we put CentOS on this cluster down here.
So right now,
Just as kind
what
of
are you running right now?
SLES.
Less.
Yeah. And we're using the Luster file system. So that's a big global parallel file system. So we got about 10 petabytes of spinning disk, really fast disk, and then about 100 petabytes of tape storage. So that's the kind of storage hierarchy. I forget how much memory there is. It's a bunch of terabytes. It's like 2 gigabytes a core, 125,000 cores, so 250 terabytes of RAM. Right, so I kind of moved this around a little bit. It's a little bit slow because we're doing the texture advection. And just, if there's any graphics people in the house, I should mention, so there's 1,600 different meshes here, but we got to do this texture advection across all of them, so we're actually doing it in screen space, which is kind of cool. And we're doing that on the GPUs, kind of on the fly. Right, so here's another CFD calculation. So basically showing a couple examples from what was Space Ops and then Exploration Misdirectorate, but now it's all lunged together into HEOMD. So we're not flying shuttle anymore. Here's a design effort to design the follow-on heavy lift launch vehicle. Right? So this is an Ares 5 design. And basically, for this particular set of calculations, they're trying to decide on the precise nose cone geometry for a heavy lift launch vehicle. So this is a common style of using the supercomputer. You just do a whole boatload, an ensemble of calculations. So this is a parameter study. Each column here is a separate geometry. These funny names, tangent, ogive, biconic, and so forth. And each row is a different Mach number, a different speed, a different point in the ascent trajectory. And then in each cell, we have just a simple rendering basically of the pressure distribution.